Yeah, hello everybody. A little bit we have to organize because next week we are starting with a little group presentations. First group presentation, I will also do then an announcement in the Moodle course. First, not first, first group presentation, Wednesday, and this is the dates. Oh, not, yep, there we are. So, 8th of April and 17:45, room to be announced. Since I will stream the presentation because you have one fellow student where we have a really good reason that she cannot participate in present. On the other way, please do not take this that you then say, well, I will be then also somewhere else. There we have a really good reason why she couldn't participate. Because on the other way, especially these group presentations, you are doing them for your fellow students. And then if we are then sitting in one room, this will be much better than compared doing this in a digital way. Okay, here, and then please for the next group presentation, please communicate then with each other, with the presenters, and they told me that for them it's on the other way not that easy to switch to another day, and maybe the students which have in parallel lectures on Tuesday afternoon, that maybe then it's possible for them, for you, that you at one day you are coming at Tuesday afternoon. So this is then something like a cooperative equilibrium in game theory. So, or in Latin, manus manam lavat. Eine Hand wäscht die andere. If you get something, then maybe you can give the next time. Yeah. So this would be nice, and also for the other groups. Then in general, for me, it's possible to do these presentations Tuesday, while the usual lecture times, or Wednesday and Thursday in the afternoon, starting at 14 o'clock. Yep. Okay. Then I was also asked, and uh, there I then also said yes, that many of my colleagues have also the idea that you have to hand in something in this semester. So I was asked if I could postpone the date where you have to hand in your personal term paper. And then I said, okay, let's move this to, I think, the 13th of May. So then you have 2 weeks more doing this. So, so hand in date for the personal term paper 13th, I said, no, Wednesday. And let's say, then, or better, then I can check this. Oops. Yeah, but this then will mean that we will do, I think, the presentations of your personal term papers then in the last week of the lecture time. So presentations of the personal term papers supposed to be, this is then 26 to 28. So not all every 3 days, but in this period to be within 26 to 28 May. Okay, especially because now I was asked 2 times for the group presentations, how you present. You are quite free, so you do not have to hand in something to me before, and it has also not to be highly elaborated. So especially there you have to do some little tasks. This you can also do by hand, and it has not everything be done with a formal editor or something else, because this also always takes some time. Okay. So anything else? Yep. Yep. Yes. Yes. This we have done. Yeah. Oh, you have left the last time a little bit earlier, and then I can. Yeah. Yeah. Yes, that's right. Uh, Let me see which group you are. Term paper, running topics. No, then it was here. And here we are. And you are Mr. Struss. So the third one, price indices. Yep. Ah, that's good point. I will put this in the Moodle course. Okay, so that's it. Anything else? So then we are already there. We are just within the linear regression, and what we are doing within the linear regression is we have some data points, some experimental data, and then we want to find, so to speak, the best linear line who fits these data points. And by I, roughly maybe this one, but we have a definite framework how to calculate this linear line, and the algorithm to do this is that we are looking at, in the vertical direction, we have a distance of every data point to our regression line, and then we are calculating all squared vertical distances. And of course, this is one possible regression line, but maybe we could also say this is maybe our regression line, and then you see, okay, then this squares changes a little bit. And what we are now want to do is that, so to speak, the sum of all these areas should be minimized. So we are just looking at, we want to use the linear line going through our data points, which is, so to speak, the best one with respect that to the aim that we minimize the sum of these area of all these squares. So this should be minimized. And then I explained to you the reasons why this is maybe a good idea doing this, because we can also do it to the power of 4 or absolute distance, or what is also sometimes done is we can define, of course, the distance of a data point to the regression line in another way, that we do not use the vertical distance, but we can also use not the the vertical, but we can also use the distance where we define the distance that this should be a rectangle in this direction. And this actually is also sometimes done. And it depends what you are doing and what your task is, what is a reasonable choice, how to do it. But the standard form is to use just the distance with respect to the vertical axis. And the explanation behind this is that this is highly related to the variance which you have introduced in your introductory course. And this variance, I told you, is highly involved in regard to the normal distribution, because you find there also this variance measure. But you cannot say that this is the best way to do it. It is a reasonable way still. Okay, well, and then in order to do this, last week we talked then about the task. What do we have then to do? Well, this just means that we have a function depending on a and b, the cut of the vertical axis and the slope, the two-dimensional function. And how to minimize a two-dimensional function is just to take the derivative with respect to these two variables and setting simultaneously both derivatives to 0. And then if we have a deeper look at these equations, then we see that these are two linear equations. So we have a system of two linear equations with two variables. And from this, we know that this is generally solvable. And if we are doing this solution, then we see we obtain these huge formulas. Well, they look a little bit complicated, but they are not that complicated. It's just the sum of all x, all y, and the sum of the product of x and y, and so on. Okay, then we did this with a little example, calculating the slope. Oops. And here the cut of the vertical axis. And well, why are we doing this? My example was that this should be historical data. So the starting question was, we have this historical data, generally positive dependence between the visits in my company and the sales volume. And then maybe we can ask, shall I hire another person so I can increase the sales volume? And then I want to have an idea. If I hire another person, and this then would maybe mean that I'm increasing the number of visits to 30, what would be then the increase of the sales volume? And this is, of course, very interesting for me in the company, because, of course, I also have to pay this additional person. And is the increase or the forecast of the increase, is this enough that I can pay this guy? Well, and what then I have to do if I want to make this forecast? Well, we have here A and B 3.92 and 1.98. A is 3.92 and B 1.98. What would be then my forecast for 30 visits due to my linear regression? Yep. Yes. Yes. 2. Yes. And this will be then, oops, 3.92 times 30. No, the other way around. 9.98 times 30 plus 3.92. So 60. How much? 3.32. Okay. Again, what we have done here is what I have already drawn in the beginning today, is that we want to minimize all these, the sum of all these red squares. This I have already done. Okay. So in order to summarize, the meaning of our regression coefficient B is just that this is the slope, and economically interpreted, the first derivative, the slope, is the marginal increase of my variable y if the variable x is increased by 1 unit. And think, for example, this could be a cost function. Then it would be just your marginal cost. And you know the high importance of marginal costs, because doing profit maximization means marginal costs are equal to the price. And this is then your supply curve to do some microeconomics again. Well, and of course, you are doing this in microeconomics or in introduction to business administration or whenever, and then you say, well, this is nobody is calculating a first derivative in practice, but this are you doing in practice. And so this is, in the end, highly relevant in your company because you have to have an idea. Where should I put my price? Okay, and then here you have to be a little bit careful interpreting this coefficient A. Well, this is the intercept of the vertical axis, and let's assume, as in our case, it is a positive number. And if this is an estimation of a cost function, then maybe you can interpret this as the fixed cost, because this would be then the cost of a volume of 0. But very often you have to be quite careful to interpret this number economically, because of course it could be also negative, and then you have negative fixed costs. And what you have quite often that you do not have only here, I think, 6 data points, but you have 100, and that in general, let's say, the most data points you find maybe in the middle in some interval. Think, for example, this is revenue data depending on some input in your company. Then over time, and it is a historical time series, then in general, your revenue and your input data will not change that much over time. So that you have really a huge interval, this is not very probable. Maybe there are some outliers, but in general, these your data points will be in some positive interval, and then this linear regression line, you should interpret this line then also only in this main part of your data. And also, in general, maybe you have a theoretical model that your data is not following a linear line, but maybe some convex function. And then, of course, the extreme values out there do not have then anymore anything to do with your company or your model itself. But on the other hand, we are doing very often this linear approximation, because you know the first derivative, or the simplest approximation of any function is just that you, within some point, calculating the derivative, and then you say, well, within some narrow interval, we can approximate, even if you have any complicated function, we can approximate within some narrow small interval our function with a linear line. So be careful. Quite often A cannot be economically remember. Maybe I'm talking always in my introductory course of macroeconomics when we are talking about the Keynesian consumption function, and then in many funny videos the autonomous consumption is interpreted. Well, people, if they do not have any income, then they still have to eat. This has nothing to do with the model, with a macroeconomic model. um, because this fit or this assumption of a linear dependence between income and consumption, this is a good assumption within some interval and not at the extreme points where you do not have any income. Okay, so this linear regression measures the linear dependence between two variables. In general, we have then a quantitative idea how the independent variable x is influencing the dependent variable y, and quite often, as we have done it, this is used as a forecasting method. Yeah, but of course, this regression can be done with any data set. And behind why we are doing this regression is, of course, the idea that I am assuming one variable is influencing the other. But you have to keep in mind this is just a mathematical calculation which can be done for every data set, even if there is no dependence in general between y and x. And then we want to ask, well, can we also calculate something from which we can deduce, well, is it reasonable to do this linear regression? And this is the so-called correlation analysis. Well, and by I, of course, again, we would by I directly say if that it is reasonable or not so reasonable to do this fit. If you assume, for example, this data set here, then of course maybe my fit is something like this. But we see that many data points are very far away from this fitted line. Or let's say I have this data set in red of the red points. And then in general, we would say it is a quite reasonable fit just by looking at it, because the dispersion around our linear line is very low. And for this, in the beginning of the 20th century, Mr. Bravet and Pearson, they developed the concept of a correlation coefficient. I think maybe in school or also in other lectures you have already heard about this. And this is in general a number which is defined in a way that for any calculated regression, this number is lying between -1 and 1. And if this number would be +1, this would mean that all data points are lying on an increasing linear line. And this would mean all data points are lying on a decreasing linear line, and very surprisingly, if this number would be 0, then actually we don't know how to draw our linear line. Then more or less every linear line would be possible. This would mean that our data set is totally symmetric, that it is just a circle or just a square. I show you in a minute some example. No reasonable linear line. Or the other way around, every linear line you are fitting would show you a 0. Okay, so how do we define this number? For this number, I have already introduced when we looked at the formulas for A and B. There we have for B also this possible presentation. And when I talked about this presentation, then we saw, well, we take here the distance of the x values with respect to the mean of the x values times the distance of the y values with respect to the arithmetic mean. And this is then called not the variance. The variance would be just xi minus x bar squared. So if we would just introduce here also an x, and therefore, if since is so to speak, you are calculating the distances simultaneously, therefore we call this number the covariance. And this covariance is in general the expected value of our random variable, and just as we have seen here, if we have a data set, in general, if we have our random variables x and y, see here, since we look at random variables, we have the capital letters, data points, there we have the lowercase letters. So we take the distance with respect to the expected value of our two random variables and then take the expectation operator overall of these two. And if we then have our data sets, oh, this has also to be an I, not a J, sorry. And this is then just defined as we have seen. And again, we have this factor here so that we have an unbiased, not dividing by n, but by n minus 1. Yeah, well, but here, when we started in this lecture with a recapitulation of what is a mean, what is distance, what is variance, and so on, there we also said taking all again only this covariance, this number or the number or the value of this covariance is also hardly to interpret because if you just change the units from euro to cent, then you have an increase by a factor of 10,000. So a much higher covariance. So because of this, we then also have to normalize this number. Actually, then we with the right normalization, we obtain then a number which is always lying between -1 and 1. And this is then done that we just divide our covariance just by the square root of the product of the variances of our two variables. And yeah, if we compare this again with the formulas here, here we are dividing for the slope only by the variance of x. Now we dividing with both variances, taking then the square root, and then we can also directly derive a dependence of this correlation coefficient and the slope of the linear regression. That the correlation coefficient is just equal to the slope of the linear regression of our data sets times the square root of the ratio of the two variances. And what we then also can show that if we are squaring these correlation coefficient, and this is then called the coefficient of determination, that this also is directly connected to our regression line. So now suppose that we have already calculated our regression line. So yi hat is just equal to a plus b xi. And of course, remember, these are, so to speak, our theoretical y values. They can coincide with the measured y values, but they do not have to. This is just the distance again between the data point on the linear line and our measured data point. So we have then here the distance of, so to speak, our theoretical y values with respect to the arithmetic mean squared divided by the overall variance of our y values. And I think this I can directly show, because in the beginning of our lecture, we just said, well, we have some data set. And now we are looking only at the values in the vertical direction, so only at the y values. And then we say, well, I do not want always to talk, I have 100 data points and always referring to all 100 data points. What have I done at first done? Well, I just calculate the arithmetic mean. The arithmetic mean is then represented graphically just as an horizontal line with the value of my arithmetic mean. And then we said, well, we use this arithmetic mean as a representation of our data set. And what we are now, so to speak, are doing with our linear regression, that we are turning a little bit this horizontal line in order to obtain a lower dispersion around this new linear line. So, and this then graphically would mean our first shot was just calculating the arithmetic mean, and now turning this linear line means now we have a somehow better representer of our data set. Do you know what I mean by this? This linear line is now, defined by these two numbers, A and B. And suppose not only 7 data points, I have 100. And I want to explain somebody else, well, what is my data set about? And then I say, well, this is quite close around this linear line y hat. And this is then, so to speak, a better representator compared to just calculating the horizontal line defined by the arithmetic mean. And the nice thing about these correlation coefficient or then of the square, and since this number is in between -1 and 1, then of course the square of the number between -1 and 1 is just between 0 and 1. And let's say, for example, that this is 0.77. And then you can say this measured with the variance is the, somehow the total dispersion of my data set. And this now, with respect to our theoretical turned linear line, this is then maybe something like a decreased dispersion with respect to y hat, to our linear regression. And then we can nicely interpret this number 0.77 that turning this linear line means that we are explaining 77%, because 0.77 is the same as 77 divided by 100, so that we can interpret this number that turning to the linear regression line means that we are explaining 77% of the dependence between y and x with our linear regression. So then this can be interpreted as 77% of the dependence between y and x is explained via the linear regression. So maybe you think that I'm talking a lot about these 2 or 3 slides here, but I remember my own statistics lectures. And there we just obtained these formulas, and within 10-15 minutes, it was said, well, we always can calculate it and go on and start doing this. And then over the time, especially when then I started to give lectures or exercises, then I asked myself, oh, well, why I'm doing this? What is the reason behind this? And because of that, maybe I'm talking a little bit more compared to other colleagues about this topic, because I want that you have an idea when you are later on are doing this. Of course, you do not have to have you do not have to explain every time. Well, I'm doing this why because of this and that, but that you maybe in general know, well, it is a reasonable thing to do this. Okay, so and if we have then this number, especially the coefficient of determination, then we can interpret somehow, but be careful. Later on, we will do the hypothesis testing. Right now, we are just calculating this number. Then we obtain 0.33, 0.2, and so on. And on a descriptive way, then in general, we say, well, if this number is lying between 0 and 0.2, then also we know that the dispersion around this linear line will be very widespread. And then in general, we would say, well, I don't see really a dependence between this. But on the other hand, it always depends on your question. There can be experiments where you are really happy that you have an R squared of 0.18. But in general, mostly you say, oh, it's only zero point 0.3. I don't know if I can interpret it that the one variable is increasing when the other one is increasing. Yeah. Uh, well, then you always have to look at very specific. Maybe you can say if you go into financial data and you have a very new product and the first data set, and this product starts within the market, and you have an idea how it should perform in the market, and then I can say, well, if you then have the first time that you have a correlation a little bit larger than 0, that you say, well, maybe there is something. Or some colleagues of mine, they have studied medicine, and there sometimes, if you ask, is this medicine, is it helpful? That there, if I remember it, this was a PhD thesis of a colleague of mine, and there they had, if I remember this right, correlation coefficients of zero point 0.3, and they said, well, this is, so to speak, the first hint that we have an effect. Yeah. Maybe actually, it depends. Well, on the other hand, if you find a number 0.85 or something like this, there we have to admit just by eye, you just say, well, this is the line which I'm fitting through my data. Yeah, but you have to be careful. Later on, we will do this. This is only a descriptive measure. So we have no causality here. Yeah. Okay. I think for the next slide, since I have talked that much already. We can a little bit faster going through this. Can I copy this? No, so I have to. I had already, I think. This one. Oops. And 31. Uh, yeah. Yep. So 237. And we have 8, 12, 15, 16, 21. 8, 12, up, 12, 15, 16, 21, up, 22. And the second one, I think this was my example. Or, oop, if I remember this right. No, this was another one. And 24, 9, 18, 8, 19, 8. So then this is this data and this is this data. So let's at first go, this is A, B, C, D. What do you think? What is R in number C? Very hard to guess, I think. Correlation coefficient. And let's even also calculate R squared. What kind of number here at C? Any idea? Yep, just one, of course, because we have 100% fit. So then R is 1 and R squared is, of course, also 1. And number D. What could be R or R squared? And the intuition by I is here very helpful. How should you put a reasonable linear line within these data set? Yeah. Yeah, it is 0 because this is of course reasonable, this is reasonable. Yeah. So in this case, this would be 0. And what do you think at A and B? Looking at A and B. Roughly, you cannot make any mistake. Okay, then let's start maybe 7.5, and then r squared would be roughly 0.5, or 7.5 is 7 times 7 is 0. Is 49, so a little bit more. And b, yep, 0.2, and r or r squared? R 0.2 minus, yeah. Because if you look at this data, a large dispersion, but if you look at this data, I think a falling linear line would be reasonable. So maybe something like this or something like this. And then, of course, if you use R, this has to be a negative. It has to have a negative sign. So let's say minus 0.2, and R squared is then almost nothing, 0.04. Let's see what we have then. So for the correlation coefficient, what do we need? We just need the product, and then the product first summing up, and we need the sum of x squared and the product of x's. So x and y, xy, x squared and y squared. So this times this, x squared and y squared. And this, we need the sums up. I'm in the German version. And now I do not have this in my mind. N times if we have the multiplication within the sum. So then let's move this just one downward. Oop. So N times the sum, and this would be then 7 times this, and also for these ones. And what else do we need? We need the product of some x times y and the product of xx. So this would mean then some x times some y and some x squared and some y squared. This is this times this and this and this one. So, and the last one, n times product minus the product itself. This would then mean that we obtain R is, sorry, R is oops, bracket, n times xy minus some xy divided by the square root of n times x squared minus x squared times y n times y squared, opening brackets, minus this one and another bracket. Hopefully this, this is, have I done something wrong? This one, this one. Does anybody know what I have done wrong? Because, of course, we have the formula implemented in our software package. So what have I done here wrong? N times x times y. This is this times this minus some x, some y. Minus some x, some y. This is not enough here. Or 2,538. No, this is right. This is okay. Hmm. Now I'm a little bit puzzled. N times xy. Where's my mistake? Let's calculate the variances separately. N times x squared. That is this minus x squared. X is n times x squared minus x squared, and for y we have this minus y squared. Now the product of both, and the square root. And here we have nxy is this one minus some x squared. No, some x times some y is this times this. If I gave you here a wrong formula, I think we make a break here because I'm done, and in the break I'm searching for my mistake. But the last years it worked. So we see then in some minutes. Okay, thank you.